everyone, Katrina here, and today we're going to talk all about scalar multiples and collinear vectors. Make sure to subscribe for more videos and definitely watch to the end to see all the examples. So let's dive in. Scalar multiples are honestly such a foundation of vectors. They really allow us to understand kind of that connection between scalar values and vector values and all their implications both in imagining the drawings of these vectors as well as understanding key algebraic points. So before we completely dive in, I just want to take a look and draw our attention to what a vector is. So very high level, a vector is comprised both of a magnitude, which means a size, as well as a direction. So we need to understand then what is that relationship between scalars and vectors? Well, a scalar is a physical quantity that just has a magnitude, whereas vector is that physical quantity that has both that magnitude and the direction. So a scalar, how does that relate to vectors? What if you multiply a scalar by a vector? Well, we can see that the direction of the vector may be affected by the sign of the scalar, and the magnitude of the vector may be impacted by the size of the scalar. So that's kind of a bit of a high level, thought of how these scalars can impact our vectors. So essentially a scalar multiple is simply just multiplying a scalar by a vector. There's nothing harder than that. You're just simply multiplying it through, and we use distribution. So let's look at some of the key aspects of what can happen. So if the scalar is positive, then the direction of the vector is unchanged. If the scalar is negative, then it will cause the vector to have an opposite direction. Note that scalars cannot not rotate vectors, so no rotation. So they can't actually change the direction, they can only make it have opposite direction. So I guess that is a change, but scalars aren't able to rotate vectors. They can only cause the vector to have an opposite direction, but no rotation. So that's just really important to note, okay? And then the other two things that we can look at is the sign. Oh, sorry, that was the sign. This is the size of the vector. So if the absolute value of the scalar is greater than 1, then that means we're stretching the vector. That means that we're making it bigger. If the scalar is between 0 and 1, then that means we're going to be shrinking the vector. We're going to be making it smaller. So I have a couple examples here prepared for us so they can show us some of these cases. So we're going to denote a scalar as some k, okay? So for this example, we have that our scalar is equal to 2. And we have some vector a, which is 4, 6. We want to calculate what is the scalar multiple if you have k times a. So what does this equal? So we simply just write out 2 and then our vector, which is 4, 6, and we just distribute it like we would any other kind of polynomial. So you multiply the 2 to the 4 and the 2 to the 6. So what do you get? You get 8 and 12. So what happens here? K is positive, so that means the direction is unchanged, and k is bigger than 1, so that means it's stretching. That means the result of multiplying by the scalar is a larger vector in the same direction. Let's look at example number 2, where k equals to negative 3. Here again, we're going to put our negative 3 in front of our vector a. We're going to distribute it as we would any normal number. So we get negative 12 and then negative 18. Let's analyze this. So our scalar is negative. That means we're in the opposite direction. And it's also greater than 1, so that means we're bigger. So say, for example, that this was our initial vector. Say that this was vector a. What is our new vector that's been scaled by k? Well, we know it's now in the opposite direction, and it's 3 times as big in the opposite direction. So we can call this is our new vector. So think about it as 3 a's altogether. So you have negative a, and negative a, which equals to negative 3a. So we can kind of visualize that graphically too. So now again, it's the same direction, same but opposite direction, and 3 times as big. Let's look at our last example over here. So we have k equals to 1 over 2. So that means we're going to have 1 over 2 times a, which is 4 6. Again, we're going to distribute it. So we end up with 2 and 3. So k is positive, meaning the direction is unchanged, but k is less than 1 and greater than 0, meaning that our vector is going to be shrunk. So it's going to be smaller than the original vector. So, when we say less than 0, greater than 0, less than 1, this can also be the same for in the negatives there. So if k is, what would that be, less than 0, but greater than 1. So again, that would be shrinking it just in the opposite direction. So in this case, if we were to draw it out, say that a is like this, we now know that the direction is going to be the same, but we're just going to be half the size. So if this was a, this would be over here 1/2 of a. So I hope that helps you get a bit of a visual representation as well as understanding the algebraic implications of scalar multiples. And really, calculating them is a breeze. We just multiply through that scalar through every single term in our vector. Now let's look at an important application of scalar multiples. We're going to explore the concept of collinear vectors. So let's look at what that means. So collinear vectors are vectors that lie either on the same line or are parallel to the same line. So if you have two vectors, a and b, they are collinear if there exists some scalar k such that a equals to kb. So we want to see, is there some number, some scalar a, by which if you multiply vector b by k, will it equal to a? And again, collinear vectors can either mean they're parallel, so that means that they will never intersect, but they have the same direction, or it can mean that it's collinear. So you have kind of a vector on top of itself, and they're touching at every point. So in that case, you have an infinite number of intercepts if it's on the same line, and if it's parallel, then you have no intercepts. So let's draw your attention over here to our example. So here we have three-dimensional Cartesian vectors. We have vector A and vector B. We want to know, are vector A and B collinear? So we know by our definition that these vectors will be collinear if there exists such a scalar k where our vector A over here, so this is our vector A, equals to some k of our vector B. So let's go ahead and set up this problem. So we learned from our scalar multiples that we can just multiply this scalar through. So let's go ahead and see what that gives us. That means now that we have vector A, which is 2, 4, negative 22, equals to negative 6k, negative 12k, and 66k. Let's create a system of equations here. So we have that 2 equals to negative 6k, we have that 4 equals to negative 12k, and we have that negative 22 equals to 66k. And now let's solve for k for each one of these circumstances to see what we get. So here, solving this algebraically, we're going to get that 2 over negative 6 equals to negative 1 over 3, which equals to k. Over here, we get that 4 over negative 12, which equals to negative 1 over 3 equals to k. And lastly, we get that negative 22 over 66 equals to negative 1 over 3, which equals to k. And hey, look at that. There is such a value for k that exists for all three of these situations. So in order for k to work, that means that we have to have the same value every time. So here we have negative 1 over 3, negative 1 over 3, and negative 1 over 3. If one of these values didn't equal -1/3, then there would be no real solution for k. But in this case, we have found such a value that allows us to have a equals to kb, and that k equals to -1/3. So that means we found a value k for this equation to be true. Therefore, that means that both vector a and b are indeed collinear. So that means, again, that they're either parallel or that they're parallel to the same line. That means that they're either the same line or they're parallel to the same line. And that means essentially that they have either the same or opposite direction. So I hope this video was helpful for you to understand the basics of vectors, understanding what scalar multiples are, and also their application in determining collinearity. Understanding collinearity is a very important aspect and fundamental to vectors because it allows us to do directional analysis. If you enjoyed this video, please drop a like and comment any questions that you have, and definitely subscribe for more videos. I look forward to seeing you. Goodbye.